So welcome to chapter 2 of this particular training, and in this particular chapter we are going to discuss local security. We've been discussing so far how to secure things which is connected, generally speaking, the cryptography pillar. Now we are going to discuss about the next pillar, the rings pillar, the privilege pillar, or local privilege pillar, code security, whatever you like to call it. So one thing I would like to mention about this particular chapter is it is not for everyone. It has a certain level of complication, certain level of knowledge, especially kernel privilege. All kind of knowledge is not really expected, but good to have. So due to some of the complications involved, I don't recommend this particular chapter for everyone. But it is one of the important things to cover. This is how local security is implemented behind the scenes. But of course, as usual, feel free to ask me any questions in case if you're finding difficulty in this particular chapter. You are more than welcome to skip this chapter and move to chapter 3 if it is finding very difficult, or if you're finding it irrelevant to the job you're targeting or the topics you are learning in terms of security. Now, in this particular lesson, what I'm going to plan to do is to give you an introduction about the whole thing. So nothing in detail we are going to discuss. That's what we are going to do in next few chapters. But here we are going to introduce the local security, what we are really going to mean by local security and the purpose of it. That's enough introduction and scare. Now let's get into the topic. So in the very beginning of the training, we have discussed there are two pillars, the cryptography and then the so-called rings. Probably I might have been calling these things different names in different times, as you will see the reason why that is the case. So cryptography, we have dealt in detail all the RSA, symmetric hashing and all sorts of things. So this whole cryptography pillar is all about securing the connection between two computers. For example, you have a computer here and you have a computer here. The encryption between, encryption in transit. Cryptography is used for encryption at rest and other non-connected security purposes as well, which we have seen, all the secrets manager, disk encryption, all that sorts of things we have seen in the miscellaneous session of the training, the cryptography. But at the end of the day, mostly it is used for hiding something from someone. So that's the use of cryptography. Now, there is another pillar right here, bit more complicated pillar, bit more difficult to understand. Because of that reason, I have not seen any training so far other than my own training, which is there in YouTube, a very rigorous approach to this particular problem, or this particular pillar is not being treated with enough focus. I have seen a lot of training on this topic, the cryptography, but this is probably more important than cryptography when it comes to the security, as you will see. And we are going to discuss the theory part, and we are going to put the concept in place before we move on to the rigorous approach like the maths we have done in the case of RSA. So we're going to understand what's the purpose of this particular pillar right here, and then we will understand a rigorous implementation of this particular pillar. So in this lesson, we are going to understand the need of this before we get into any implementation or how it is done. First, we will discuss why it is done. What's the purpose? What is the problem we are solving by this particular pillar? That's what we are going to discuss more or less in this lesson. And in the next lesson, we will see how it is done. We'll take a very specific example of a 32-bit Windows operating system kernel. The reason why I'm taking this very rigorous, very dry, very rigorous session, which I have already taken, I'll be just annotating my own training, which I have done some 10-15 years back. So that we will do in the next lesson. But in here, we will put the perspective of what is the requirement of this. So let's get into it. So let's take an everyday example. So you have your Chrome browser here. Could be any mobile application or anything for that matter. Let's take the example of a Chrome browser. And in the Chrome browser, you have this tab 1. This is tab 1. And then another tab 2, 3, and then so many other tabs. Suppose you have opened a chat application. This is a chat app in tab 3 chat. Say Facebook or Instagram, something social where the other party has access to that particular conversation. Now in the tab 1, so you have the tab 1 here. In the tab 1, you have your bank account open. All your transaction details, all your bank account details are open in the tab 1. And in the tab 2, you have a chat application. Now the question for you is that how the application, so there is an application, there is code running in both tab 1 and say tab 2 or tab 3. And this is a very secure application running here. For example, if I give the right keyboard and mouse interrupts to this particular application, you can do transactions. You can move the money from one account to another account because it's a banking account I have opened here in tab 1. Say for example, an ANZ bank account opened in tab 1. Now the question is the code running. So there is code running inside these other tabs and there is code running in tab 1 also. How you make sure that the code running here is not accessing this one particular thing right here? Have you ever thought about it? The code is running here as well. So let me show you the code in 2 different websites, for example, to show you the code which is running in 2 different applications, which is there in 2 different tabs in a browser. So I have 2 tabs open inside my browser here. So this is an Edge browser, which is similar to Chrome. First page, I have opened my Wikipedia page right here. Some random Wikipedia page I have opened. And another is YouTube here. Now the question is the code running inside this YouTube page, how it is making sure that it doesn't have access to this particular page or the data inside that particular page, and it cannot send keyboard and mouse interrupt or capture a keyboard and mouse interrupt from this particular page. That's the question. So let's see the code first. If you want to see the code of this particular thing, you can go to more tools, developer tools, and in here you can see all sorts of things this particular website uses to display this particular page. As you can see, this is the HTML and there is this JavaScript running. You can put breakpoint and it's just like any other code. You can edit this code if you want right here. So all these script tags are potentially JavaScript executing different amount of code for different purposes. And this is a code of this particular page right here. Let's see that. More tools, developer tools, Control-Shift-I will do if you want to use the shortcut. Again, you can see script. Let's assume that HTML is harmless and doesn't do much, or CSS for that matter, but otherwise there is code running here. These are programs, pretty much computer programs running here. Now the question is how this is isolated from one to another. The implications are very high. This is a high stake thing we are talking about. If your bank account is being accessed by a different website running in the browser, you have huge amount of problems. So the applications are completely isolated. Let's get back to the Blackboard. So what we are talking here is essentially multitasking. So operating system multitasking or multiprocessing is probably a little bit an umbrella term these days. There are a lot of things comes under this particular name right here. So for example, virtual machines, VMs. Virtual machines are nothing but different tasks or processes running inside a hypervisor. Same technology. Tabs inside the browser. Tabs in browser. Then operating system process, OS process. We'll see that. Docker containers or containers in general. Application containers. Mobile applications, which are nothing but processes. Mobile applications, processes. Then there are a class of things called virtual machine for the runtime, for example, JVM, Java Virtual Machine. So this virtual machine is different from this one. This is actual machine itself, but this is more of a runtime. For example, the .NET runtime, the Python runtime, all the application runtime, most of them has something called garbage collection. We'll get into the details later, why they have this isolation technology built inside them. But the idea is one single hardware you have. That's what is common in all these items listed above. you have one single computer here, which has a memory, a CPU, and potentially a disk and a lot of other devices, graphics card, network card, and all other kind of things sitting there. So you have a single hardware and running different programs in it, which is multitasking at the end of the day. Whatever name you like to call it, multiprocessing, multitasking, doesn't matter. You're running different computer programs within a single hardware. For example, VMs. If you take virtual machines, easy to instance in Amazon, or Azure virtual machines, or virtual machines in Google Cloud, or virtual machines running in a VMware vSphere. They are all simply processes running inside hypervisor. Hypervisor is installed into the hardware, and each virtual machines are simple processes within the hypervisor. Now, tabs inside a browser, most of them these days are different processes, but either they are processes or they have these runtime isolation as well. We'll discuss about these runtime isolation, but they are again different processes, different code running inside a computer. We'll see some of these processes shortly. And processes, the name itself is all about application isolation from one program to another. And this is what we will discuss. Pretty much all the other thing uses the same technology, same concept to isolate the application from one program to another. Docker container or the container, they are nothing but processes again, just like the VMs, just that it has more bells and whistles. Mobile applications, again, different processes within a Linux operating system. So the fundamental idea here is that you have a single hardware, you have a single computer right here, and you are running multiple different independent programs inside that. And each program behaves and thinks like it is the only one running in that system. Any attempt to access the other program running inside that will be denied. And a lot of security is built on top of this. The file system security, the process security, everything, pretty much every security within a system, within a computer is maintained using this particular approach, what we are going to discuss. And one of the most important thing here is that each process is running inside the hardware. Let me draw that in a different color. So these are the different software processes running. They are independent of each other. These different programs running inside the same hardware, they themselves has role-based access control. They have themselves rule what it can access, what it cannot access. Or we can say that each of them has a privilege. So the privilege of each process is different. And when a process which doesn't have enough privilege and it tries to escalate that privilege to a different process which has more privilege, that is called privilege escalation. It's one of the main attack vectors when it comes to cyber attacks and things like that. So we'll discuss that, all sorts of things. But what we need to understand is that you have a single hardware with a CPU and memory and disk and other hardware devices, a single computer. And inside that, you are running multiple programs. It could be virtual machines, it could be Docker containers, it could be processes, it could be tabs inside the browser, doesn't matter. Different computer programs you're running. Computer programs have different privileges. They can do certain things, they cannot do certain things. Some process can do anything, some code, like for example, the kernel, the hypervisor. Certain piece of code we will discuss can do anything. They have God level access on that computer. They are the master of this particular hardware. We'll discuss such kind of code. Some doesn't have any permission at all. They are sticking to very simple task. So these different code has different permissions or privilege, and they are supposed to obey that privilege, and they are not supposed to jailbreak and do what it is not supposed to do. Very important. What if that application, the chat application which is running in the other tab, escalates its privilege, jump out of the jail which is present and get to the accounting, the bank account tab, what will happen? It can compromise the bank account and transfer the money. So it is very important to understand the privileges of different processes and how it is implemented. Before we getting into the implementation part, like I was saying, I'm trying to put forward the requirement we are trying to accomplish here. So it's all about isolating different pieces of code running inside a single computer. That's all about what we are going to discuss. The reason why this is more important than cryptography is that these are more vulnerable points. If some of these things are compromised, the whole system easily get compromised and the whole data get lost. Same with cryptography, but these are more vulnerable in terms of attack surface. Now, at least to explain this whole thing from the periphery of the concepts, we need to get into the boot process of a computer system. So let's draw the computer system first. So we have the system here in the big box, which I'm going to draw right now. So this is the system, the whole hardware, in which we have the most important part, which is the CPU. This could be 1 CPU or 100 CPU, doesn't matter. We are going to put it the CPU. When I say CPU, what I mean is the chip which execute instructions, not the box which we see outside a computer. So that's just the ATX cabinet, if you're thinking about it. But there is a chip inside from Intel, AMD, or some other company, which has instructions executed within that particular chip. That's what I mean by CPU. Then there is this memory. Memory is again another chip. If you want to have some more information about the basics of all these things, please visit my basics computer science training. But memory is another chip, and disk could be a chip or a disk. It's a secondary storage. And mostly, almost all the hardware have one or more network cards, NIC, and then graphics card, mouse, keyboard, whatnot. But these are the main things or the main hardware items we have. Now we have a power switch on this computer. So this is the power switch. Let me draw that in a different color. So this blue button right here is the power switch. Now what we are going to explain in a nutshell is what happens when someone powers this thing on. What happens? That's the idea we are trying to bring here, especially from a security perspective. Now one of the things to notice here is that the hardware itself, the CPU, I purchased a CPU from one of the stores here, for example, or a memory, and assembled a computer, and it doesn't do anything at all. It's more than useless until and unless I install an operating system. So most of the laptops you buy or the phones you buy, they are computers. But in most of them, an operating system as well as all the bloated application is pre-installed. So you may not know what I'm talking about. So feel free to watch my basics computer science training if you are new to building a computer and things like that. But at the end of the day, if you buy a CPU, an Intel or an AMD CPU, and RAM and disk and all those things, and if you assemble a computer, it doesn't have anything at all. If you switch it on, all you get is an error. There is no boot disk. Let me write that error down here. No bootable disk. That is the error you will get when you turn it on. And that's it. You don't get any more past than this particular error. This is the error you will get if you buy a CPU, memory, disk, and all the other hardware and push the power button. This is the error you will get. Now, how to escape from this particular error, or how to solve this error? So we need to solve this particular problem. No boot disk. So we need to create a boot disk. What is a boot disk? Boot disk is normally a disk, a bootable disk, which has an operating system installed. What is a bootable disk? Bootable disk is nothing but a disk which has something written in its boot sector. So there is a part of disk, mostly the first sector and things like that. Don't want to get into the details of it, but a part of this particular disk will have a program which tells how to load an operating system into the hardware. So what is operating system? Operating system is nothing but a program, just like any other program. And the operating system manages the whole hardware. That's the purpose of the operating system. It knows how to interact with this hardware. For example, the CPU. The specification of CPU, the modern CPU like the AMD or Intel CPU, for example, the Ryzen 7. In this laptop, I think I have Intel generation 7 or 11. I don't know. I need to check. But one of those CPUs. If you look at the specification of that CPU, you will understand that it is almost 4,000, 5,000 pages of PDF files. I'm showing that in one of the presentations in the basics computer science training. But at the end of the day, all these devices we are talking here, all the CPU, memory, disk, NIC card, keyboard, mouse, graphics card, all these devices are so complicated. Thousands and dozens of thousands of documentations and details to handle them. All that complication is built into the operating system code. You can think of it like a single program for the time being, but it's a combination of a lot of programs and a lot of modules and things like that. Doesn't matter to us, but at the end of the day, all it does is handling the complexity of the hardware. At least one of the things it does. There are so many other things it does. We will discuss that, especially from the security perspective. But for the time being, the most important thing it does is handling the computer hardware. Coming back to the boot disk. So the first thing you do after assembling a hardware, so you purchased your CPU, memory, say for example, you ordered it from Amazon or Scoptech, doesn't matter. Some shops, you got all these things, you assembled. The next thing you do is install an operating system. How do you install an operating system? Using a bootable USB drive or a bootable disk or any bootable device, mostly a read-only or USB device you use to boot from that and install an operating system. Now, once the operating system is installed, it creates a boot sector and boot partition and all sorts of things and creates a bootable drive with the operating system and all the necessary programs, the basic programs installed in it. The examples of operating system you might be knowing: the Windows operating system, the Mac, iOS, Android, Linux, all different operating system we already know. At the end of the day, they are completely software, they are programs, they are instructions at the end of the day, mostly written in a C programming language. Most of the operating system has been written in C programming language, or part of it has been written in C++, and these days Rust programming language comes into the picture. But at the end of the day, these are code binary instructions for CPU. At the end of the day, in simple terms, operating system is nothing but a program which executes inside the CPU, which controls the whole hardware and making the life of normal people like me and you easier. That's the purpose of the operating system. Now let's discuss the security aspect of this whole thing. So again, we have the hardware. I'm going to draw one box this time. And this is the start button of the computer. So this is start button. So I'm going to press the start button. So start button is getting pressed. What happens? The boot happens. So the disk is there here. The CPU will read from the boot sector. There are a little bit of stories around BIOS, and BIOS is handing over to the operating system through the boot disk and all sorts of different details, but it doesn't matter to us much. Now the boot is happening right here. What is the boot process? The boot process is, or the operating system loading process. You might have seen when you restart a phone, an Android phone or an iOS phone, it takes a lot of time. When you restart it, at least a couple of seconds. Even the best phones take a couple of seconds to load. Windows takes very less time these days. So does Linux. I have seen Linux booting very fast. But at the end of the day, what it does is, this is the CPU and this is the disk. And disk has this boot sector and the operating system installed. Let me draw the operating system in a different color. So the green color is the boot disk or the boot sector. And most of the boot disk has the operating system as well. This color is the operating system. That disk can have other things as well, but mostly it has the operating system. And we have the memory here. The memory is here. Most of the things happens is loading the operating system in the disk to memory. That is what happens when you turn on a phone or turn on a device like a computer or a laptop after shutting it down. This is what happens. Now this program is getting loaded into the memory. So this is the memory. And in parallel, it is being executed in the CPU as well. Very important. There is execution happens in the CPU. In fact, everything is done by CPU at the end of the day, including loading the disk to the memory partially. I'm not very rigorous in terms of this particular discussion. If you're an expert or something, for example, I'm not discussing any DMA, direct memory access, and all sorts of things. I'm ignoring all those details, and it is most like a bird's eye view of the whole thing. In the next presentation, we will be very solid and the rigorous approach will be done in the next lesson. But at the end of the day, when you load an operating system, what happens is loading whatever is in the disk to the memory, the volatile memory, and executing the relevant parts inside the CPU. That's what happens when you boot up a system. Everything starts from the boot sector. The execution starts from the boot sector and it continues through the rest of the operating system. That is what happens in a nutshell when you power this thing on any computer, for example, a phone or a laptop. Now, I want to introduce a concept called privilege of a code or a code privilege. So code privilege is slightly different from the privilege I discussed before. In fact, code privilege is used to develop the rest of the security in a computer, which is what we are going to discuss in the next couple of hours. The code privilege, it's very difficult to understand because it's deep down in the hardware it's implemented. The privilege of a code or the privilege of the EIP register, if I talk specifically in the Intel x86 architecture. That's what we are going to deep dive in the next lesson, but I want to introduce the concept of privilege of a code. So at the end of the day, privilege is nothing but what you can do and what you cannot do. It's all about that. Privilege is all about that. Now, I said that the operating system is code. At the end of the day, they are instructions to the CPU. They are software. They are binary machine code compiled from programming languages like C or C++ or Rust these days. Now that code which is running inside the CPU has a privilege. The code which is part of the operating system, which is executing at this boot level, they have almost God level privilege, which means that they can do anything to this particular hardware. If the hardware supports, this code will be able to do it. This is true for the 90% of the operating system. The code we are loading here, the code which we are calling the operating system, 90% of the code has the full privilege or the God level privilege in an operating system. Now there is a name for this particular piece of code which has full permission on the hardware. I'll give you some examples in which it does and what the privilege, the non-privileged code doesn't have. I'll give you some examples. But the code which is getting executed while the system is getting boot up, the initial code, the operating system code which is getting loaded, almost always has the God level access, full access, the complete privilege. I wouldn't call this admin. Admin is a different thing, or the root is a different thing. That is the process privilege. We'll discuss about that later. The privilege escalation normally happens at that level. This is even higher privilege than a root or an admin. Now, what is the name of this particular God here? This God is called kernel mode or kernel. So the part of the code which runs inside the CPU, which has full privilege or full permission to execute any instruction of the CPU, is called the kernel. Let me define that. If anyone has given any other definition for kernel, forget it. You can just take this definition to the bank. Let me repeat that particular word or the definition here. The kernel. The kernel is a set of code, a set of programs. When you execute that program, you have the full privilege. Anything the CPU can do, that code will be able to do. This is not administrator. This is not root. We are not talking about root and administrator. I'll give you the difference shortly, but I want to tell you that this is not the admin root privilege we are talking about. That's a process privilege. In fact, the process privilege is implemented using code privilege. So kernel executes with the full privilege. It can execute all the instructions in the CPU. Now, in the case of virtualization, this kernel is also called hypervisor. Hypervisor, kernel, it's all more or less the same thing, at least from our discussion perspective. They are slightly different things, but in our discussion perspective, it's all same thing. Now let's talk about the code which doesn't have the full privilege. So one of the first thing it does, the privileged code or the kernel, let's call it kernel. So kernel is loaded into the memory. One of the first thing it does is it creates programs which has a less privilege. That programs is called user mode or user space. User space is more used in Linux, user mode in Windows. Doesn't matter. At the end of the day, we are talking about code which is having less privilege. So who is creating that? The guy who is having the privilege, which is a kernel. Now let's take example of all these things to understand what we are talking here. First, I would like to give you an instruction in which only the kernel code can execute with full privilege. This is a very typical instruction I give for this particular example is STI, a set interrupt flag. CLI, clear interrupt flag. These two instructions, these are instructions for a x86 Intel CPU or even AMD CPU. I'm pretty sure there are similar instructions for ARM and all sorts of different CPUs because it's one of the basic concept in any platform. Basically, this is clearing the interrupt and setting the interrupt. We'll get into interrupt shortly because we need to get our head around interrupts to understand this whole picture. Now, why I'm bringing up these instructions here? The reason is these instructions cannot be executed without privilege. For example, if you do a set interrupt flag, STI in kernel mode, there won't be any issues. But if you are executing from a non-privileged code, for example, a Word application or a Notepad application or a web browser, doesn't matter even if you have admin permissions or not, admin privileges or not, you cannot execute an STI instruction or a CLI instruction. What will happen? The application will crash and the control will automatically get transferred to the kernel. And interrupt, a software interrupt will get generated. We will get into it shortly, but in summary, without the correct code privilege, you cannot do certain operations on the CPU. There are so many operations like changing certain registers, like the control registers, certain flags inside the CPU. Basically changing the state of the CPU in certain special places is allowed only from the privileged code. Now this is a technique all the CPUs in the world, doesn't matter it's ARM or x86 or AMD 64, doesn't matter which platform we are talking about. This particular piece of information or technique is used every single place in different forms, pretty much. Now in the next presentation, we will discuss how this is really implemented. This has a very complicated implementation, at least to explain and grasp in the beginning. Once you get a hang of it, it should be fine, but otherwise it has a very rigorous implementation with a lot of flags and a lot of things comes into the picture, a lot of registers, a lot of moving parts at the end of the day. Basically, the memory management implementation, the security of the memory management implementation is what we are going to discuss in a typical operating system. So all I wanted to do here is to introduce the concept of code privilege, which is different from admin privilege or root or anything else. The code privilege is normally comes in only two flavors. Very simple, two flavors. In fact, three flavors people say: the hypervisor, kernel, and the user mod. But let's keep it simple. I like to say hypervisor is just another kernel, although people say it is ring -1 and all sorts of different things, but the concept is exactly the same. In fact, the x86 platform implementation, the memory manager implementation, has 4 privilege levels, but we don't use any of it. We just use 2. The user mode and the kernel mode. The kernel mode can execute any instruction of the CPU. Examples are STI, CLI. There are so many other instructions, certain type of move instructions and things like that. These operations, if you execute from user mode, you will get an exception and an error. So you need to have God level privilege or kernel privilege to execute these instructions. This kernel and user mode privileges, the difference in these two things right here, is the core of the implementation of our pillar 2, the second pillar we are talking about. If this is compromised, pretty much everything we know as of now is compromised, starting from your mobile application to your bank accounts to pretty much anything and everything. So again, I have not explained how this code privilege is coming into being and how it is being implemented. That part I have not explained. I'm only saying that there are things called code privileges, and to execute certain instructions like STI, we need to have special code privilege, which you see, kernel privilege. If you execute those kind of instructions, they are called privileged instructions. So these instructions are called privileged instructions. And if you execute such instructions from user mode, what you'll get? You'll get an error and your application will crash. Basically, it generates something called a software interrupt and switch back the control to the kernel. Also, we have said that everything in an operating system like Windows or Linux or ESXi or anything like that, a hypervisor, is implemented. The entire security within a computer, within a single piece of hardware, is implemented using this particular concept right here. Everything is built on top of this. This is like the cryptography, the base layer of security within a system. So we have seen some of the details around the local security, the code privilege. Now what we are going to do is we're going to dive deep into this particular topic, get as metal as possible. So let's get into that topic, and I'll see you in the next lesson. Thank you.